I'm going to talk a bit today about extremal graph theory, which is a topic I've been thinking a good bit about over the last couple of years. There was a survey. There's a very nice survey about 5 years ago by Zoltan Faredi and Mickey Shimonovich, talking about all the results that are known in extremal graph theory, in particular determining the extremal number of bipartite graphs. So I'll define all this in a second. And somehow in the last 3 or 4 years, this area has been almost completely rewritten. And I'm going to talk about some of the things that have happened. So in some ways, this is more like a survey talk. I'll talk a little bit about my own work, but I'll also talk a lot about some of the things that other people have done along the way. Okay, so do shout at me as well. Sometimes the screen can stop or stops updating. So if that happens, just shout at me. Okay, so the definition, the main definition that we're going to be dealing with is just the extremal number. So the extremal number, NH, is the largest number of edges in an n-vertex H-free graph. In n-vertex. Okay, so, and the classical result there, or the sort of oldest result there, is this result of Mantel, so from 1907. And there, the result is that the extremal number of triangles is just n squared over 4. So rather the floor of n squared over 4. And the example there is just a simple example where we take two sets, each of size n over 2. We put a floor sign on one of them and a ceiling sign on the other, and then we take all possible edges between them. Now, that clearly doesn't contain any triangles, and it's as large as possible without containing any triangles. This was generalized some years later, so there's a theorem of Erdős and Stone, which, when tied with an observation of Mickey Shimonovich, basically gives a characterization of the extremal number for all graphs. So their theorem is that the extremal number for any h is 1 minus 1 over the chromatic number of h minus 1 plus little o1 times n choose 2. So here chi of h is just the chromatic number, and the way to think about this is that if you have chromatic number h, then you can avoid a copy by just taking chi of h minus 1 blobs, so sets, and putting all possible edges between the different sets. So oops. Okay, so and then, for example, here, sorry, I keep doing that. So for example, here we have no K5 because K5 has chromatic number 5, and there are only 4 parts. So 2 of the vertices would have to go in the same part, but there's no edges inside any of the parts. And that simple construction is sharp. That's what this Erdős-Stone-Shimonovich theorem says. Okay. What we're going to be interested in today is the case when the chromatic number is 2. So we're going to be interested in bipartite graphs. And as I said, bipartite graphs are exactly the case when the chromatic number is equal to 2. So that means that you have 2 sets, and all of the edges lie between the 2 sets. There's no edges inside. So everything is sort of between one set U and the other set V. Now, in this case, the problem becomes a lot more difficult. Well, in some sense, it's simple because the Erdős-Stone theorem tells you that, so corollary of Erdős-Stone, is that if H is bipartite, then the extremal number satisfies is little o n squared. But the thing that happens is that once we have proved one bound, we want to then know what happens at the next order. So actually, just knowing that it's little o n squared doesn't tell you very much, because it could be anywhere between n and n squared. There's a slightly better theorem due to Kuvari, Schoch, and Turan. So Kuvari, Schoch, and Turan have shown that in actual fact, this is from maybe 1954, that if H is bipartite, then there is a positive delta such that the extremal number of NH is bounded above by some constant times n to the 2 minus delta. So you can always drop by some power saving. Not only do you get some little o n squared, you actually get a full power saving on the bound. In actual fact, what they actually prove is, so there's a few special cases of this that are somehow much studied. So let me just state the two cases that have received the most attention. One is when the particular graph H is a complete bipartite graph. So when it's KST and KST lies between, so that KST just means you have S vertices on one side, T vertices on the other, and you join absolutely everything. So complete bipartite between S things and T things. And in this particular case, actually, the Kuvari-Schoch-Turan theorem tells you that you have big O of n squared minus 1 over S. And it's known that this is sharp. It's tight for T much larger than S. So somehow when T is much bigger than S, this is a sharp bound. And the other case that's been studied a lot is the extremal number of even cycles. So an even cycle is just of length 2k, is just 2k edges in a row or 2k vertices in a row in a cycle. And in that case, it's known that the extremal number actually drops off to 1. So somehow it becomes easier to find longer cycles. So the extremal number is at most some constant depending on k times n to the 1 plus 1 over k. And this is tight as well, but it's only known to be tight for k is equal to 2, 3, and 5. Somehow the other cases, we really have no idea what's happening. Solving either of these questions would be a major breakthrough. Sorry, in the second case, it's obvious what the question is. So the question here is just, can you extend this so that it works for all k? And the question here is, can you push this t down close to S? So in their original paper, Kuvari, Schoch, and Turan actually conjectured that when S is equal to t, you should still get a bound like this. Okay, so I'm going to try and say a little bit first about this particular case of KST. So what happens in that particular case? Okay, so here's a construction. Oops. So let's take a bipartite graph between two vertex sets, U and V, which are both copies of FQ squared, where FQ is just a finite field with where Q is a prime power. And we join, say, AB, an element of U, to XY, an element of V, if and only if their dot product, so AX plus BY, is equal to 1. And actually, if we do that, this graph has how many vertices? Well, it has twice q squared vertices, because there's q squared vertices on each side. And it also has, so each vertex has basically q neighbors on top. So it has some constant times q cubed edges. And it also has no k22. And actually, k22 is also the same thing as a C4. And the reason for this is simple. So what we've done here is, if you fix A and B, then the things that A and B are joined to are just correspond to a line on the other side. So if A and B are fixed, the collection of things it's joined to is the collection of xy, such that ax plus by is equal to 1. So it's just a line. So for every pair A and B, I have my copy of fq squared on the other side, and AB gives me one line on the other side. Some other A prime B prime gives me a different line on the other side, and any two lines intersect in at most one vertex. So that means that any pair on the side U have at most one vertex in common on the other side, simply because two lines intersect at most once. So that's actually quite a simple construction. That gives the sharp bound up here when s is equal to t is equal to 2. And here it also gives when k is 2. It also gives the correct bound. Okay, you can give a similar construction for k33 as well. So this is a construction due to Brown, I think. And instead we let u equal v equal fq cubed, and we join ABC, an element of u, to xyz, which is an element of v, if and only if. Now, before we talked about lines, here we actually do spheres. So x minus a squared plus y minus b squared plus z minus c squared is equal to 1. So basically, again, we think of it as, if you fix A, B, and C, then what you get on the other side is you get that this is connected to a sphere of radius 1 on the other side. Now, if you cheat slightly, and you think about this in terms of what happens over the reals, then over the reals, if you have 3 spheres of radius 1, those 3 spheres intersect in at most 2 points. Okay, and actually you can carry that intuition over to finite fields. You need to be a little bit careful. For example, this doesn't quite work unless you assume that Q is congruent to 3 mod 4. So you take a prime congruent to 3 mod 4. But if you do that, then this intuition I gave actually gives you the right thing, and this has the right size and the right number of edges, and actually gives the sharp lower bound for, again, for this, when s is equal to t is equal to 3. Okay, so obviously the thing to do now is to just generalize this, right? So, and the generalization is, in one sense, or in some sense, obvious. So if we're talking about s, then we would like to take u and v to be fq to the s. So that worked well when s was 2 and when s was 3. So if we take u equals v equals fq to the s, and we join x equals x1 up to xs in u, to y equals y1 up to ys in v, if and only if f xy equals 0 for some appropriate f goes from fq to the s cross fq to the s to fq. So somehow all we have to do is choose the right polynomial here, f. Unfortunately, that seems to be a difficult thing to do. So you can try and push this through. And if you push it through, it is possible to push this through. What you end up with is the theorem of Kolar, Ronyai, and Szabo. from about 96 or so. I'm not sure of the date, so I won't write it down. And what they show is that for every S, there exists a T such that the extremal number of n kst is equal to omega, so it's greater than or equal to some constant, times n squared minus 1 over s. So this is the thing I alluded to a couple of pages ago, that when t is much larger than s, you can get a matching lower bound. It's reasonable to expect this, actually. So the reason being that up here, if your f has degree d, then the intersection of s things will actually have size around d to the s. So realistically, the best you could really hope for is if each of these linear polynomials won't work, just because they intersect. There just aren't enough of them, essentially. But if, say, this was quadratic, which again can't quite work, but if you could choose these to be quadratic, then you'd have 2 to the s intersections, which is reasonable, but it's still large. And actually, what Kolar, Ronyai, and Szabo get, so Kolar, Ronyai, and Szabo take t greater than or equal to s factorial plus 1, which was improved very slightly by Alon, Ronyai, and Szabo to t is greater than or equal to s minus 1 factorial plus 1. And that's where things remain. So that result was proved in about 98 or 99, and that is the best lower bound that's known. So even though it's conjectured that when s equals t, there should be some construction, the best that's known is actually when t is at least s minus 1 factorial plus 1. One interesting aspect of this is that when s is 2, we just get t as 2, and when s is 3, we just get t as 3. So actually, it corresponds to the two simple constructions I gave on the previous page. Okay, so the thing that I wanted to actually mention today, or the first thing that I really wanted to say that's at least relatively new, is there's a key idea. And actually, the idea goes back to some work of Matuszek, but I think was probably come up with independently by Blagojevich, Buk, and Karasov, and then developed further by Boris Buk. And the idea is, in this construction up here, so this sort of generic construction where you want to find an f for which this works, it's a good idea to just choose your f randomly. So the sort of key insight is that you can choose f randomly. And what I mean by that is you're choosing a random polynomial over a finite field, and basically what you're doing is you're just choosing coefficients randomly. And if you choose the coefficients randomly, it turns out that it has nice properties, and you can prove this Kolar-Ronyai-Szabo theorem. Now, the situation is such that you have less control over what this t is, but you still have some control over what this t is. And it turns out that this is much more malleable. So some of the things that I want to talk about today is the fact that if you use constructions of this form, so this has become what's called the random algebraic method. So if you take constructions of this particular form, then it turns out to be very malleable, and you can prove lots of things. So let me start with an example, and the example I'll talk about actually goes back to cycles. So for cycles, I said already that that we know that the extremal number of n C2k is bounded by n to the 1 plus 1 over k, and that this is known to be sharp when for k is equal to 2, 3, and 5. You can actually generalize this. So you can define a graph called theta k of L, and this is a graph that has L disjoint paths of length k between two fixed vertices. So in particular, theta k2 is just a cycle of length k. Because if you think about it, if you fix two vertices, and I take, say, two paths of length 3 going between those two vertices, then all I've done is I've formed a sixth cycle. So, and for theta of k3, then I'm just adding another one between. So the reason it's called a theta graph is that if I add another path of length 3, then I get something that looks like a theta. Okay, so even though we only know, so we know that xn c2k is omega of n to the 1 plus 1 over k when k is equal to 2, 3, or 5, this theta graph sort of is a natural development or a natural generalization of cycles. And in fact, there's a nice result of Jason Williford and Jacques Verstraete. So Verstraete, Williford, saying that actually the extremal number of theta 4, 3 is what it should be. So it's omega of n to the 5 over 4. Why is this interesting? Because so theta 4, 2 is just C8. And we don't have a lower bound for C8. So we don't have a matching lower bound for C8. So what Jacques and Jason show is that actually if you take instead 3 paths of length 4 between two vertices, then you do get the right lower bound. And they have a very specific construction that gives this. So using the random algebraic method, you can prove something more general. So there's a result by myself which says that for all k, there is some L much larger than k. I don't really have any good control on how large k is, such that the extremal number of theta kl is at least what it should be. So n to the 1 plus 1 over k. So again, even though one can't show that there are graphs of that size where any 2 points have at most have at most one path of length k between them, what you can show is that there's a construction of the right order where any 2 points have a bounded number of paths of length k between them. So that's what this result is saying. And I know of no way to prove this result that doesn't go through using the random algebraic method. So you seem to, well, at least at present, we need something like that to get a result of this form. Okay. The second result I will mention that uses this random algebraic method relates to a famous conjecture of Erdős and Szymonovitch called the rational exponents conjecture. Due to Erdős and Szymonovitch. And the rational exponents conjecture just says that for any rational number, any rational between 1 and 2, there is a bipartite graph H of R such that the extremal...
David, there is a question.
Oh yeah, sorry, I couldn't see.
Is the upper bound for theta KL is the same as for C2K, right?
Yeah, sorry, yes, I forgot to mention that. Yeah, so that's exactly right, that the upper bound is known to be exactly the same. So so let me just add a note here. So it's a result of Fodry and Szymonovitch from the early 80s saying that that xn theta kl is big O of n to the 1 plus 1 over k. So for any L, there's a constant inside the big O term. In fact, that constant has been closely studied by Boris Buch and Michael Tate who've proved some very nice results about how the constant depends on L. In fact, they've determined the correct dependency on L if k is odd. It's kind of a strange thing that it works for k odd, but not for k even. Okay. All right, so getting back, the rational exponents conjecture says that for any rational OR, there should be a bipartite h of OR such that the extremal number of h of OR is asymptotic up to some constants, n to the OR. So the form should be, so if I choose my favorite rational 3/5, or sorry, should between 1 and 2, 8/5, then there should be some graph for which the extremal number is asymptotic to n to the 8/5. Okay. There's actually a conjecture in the opposite direction as well. So rational exponents conjecture 2, again due to Erdős and Szymon. And that conjecture is that for any bipartite h, it's basically the converse. So for any bipartite h, there exists a rational OR such that the extremal number of nh is equal to theta of n to the OR. But I believe this first conjecture. It seems completely plausible to me. I think this second conjecture is just not true. Couldn't possibly be true. I don't know how to disprove it, but I'm fairly certain that it's not true. Actually, while I'm at it, or while I'm about it, let me state one of the other big conjectures in the area, which is the compactness conjecture. Again, due to Erdős and Szymon. And it says that if h1 up to hk are bipartite, then the extremal number of the family of graphs h1 up to hk is determined by, so it's basically theta of the minimum over k of the extremal number of n, minimum over I, say, of the extremal number of hi. So that's basically saying that if you have some finite family, it's not true for infinite families, if you have some finite family of graphs, then the extremal number for that family, which just means when do you get one of them, should be just determined by the extremal number of the minimum of that family. Again, so both of these, and I might get, depending on how time goes, I might get back to this at the end. Both of these are known to be false for hypergraphs. So if they're false for hypergraphs, I see no particular reason why they shouldn't be false for graphs as well. Okay, so how does this random algebraic method impinge upon these questions? So I'll forget about the second questions, but there's a theorem by myself and Boris Buch, and the theorem says that for any rational between 1 and 2, there is a family of graphs, h of OR, such that the extremal number of h of OR is theta of n to the power of OR. So the only difference between this and the conjecture as stated by Erdős and Szymon is that we don't get a single graph. We get a family of graphs instead of a single graph. And it's still open to try and reduce this back down to single graphs. Essentially, the problem is a funny one. So what we get is a specific graph, but then we have to allow all of the degeneracies that could happen. So if you have a particular graph, say, like a cycle of length 8, for example. So you have the cycle of length 8, but you have to allow all of the ways in which this could collapse on itself. So it could be that even though you have that cycle, you have this goes up here, but then this comes through and intersects in the middle. So And in our family, even though we start with a specific graph, we have to allow all of these possible degenerate configurations. And the problem there is something that I tend to call the degeneracy problem, which is to try and rule out these degenerate copies, or to show that at the extremal number, or at what we think is the extremal number, we can get copies of things, non-degenerate copies of various things. Okay, so as it stands, this is where things sit. Okay. All right, so I'll say more about this later. For now, I'm going to switch to a different topic. Actually, it looks like a different but I'll come back around to this. So there aren't that many general results in extremal graph theory. One is a nice result of Faraday, and it says that for any bipartite graph, with max degree or on one side, there is, any bipartite graph H, with max degree or on one side, the extremal number of n of H is big O of n squared minus 1 over R. This actually includes, for example, includes K or S. So if I take K or S, where I have one side of size R and the other side of size S, then everything up here has degree R on bottom. So in particular, the extremal number will be big O of n squared minus 1 over R. And actually, we know that's tight. So this thing is tight if H is equal to K or S, and S is much bigger than R. Just by using that Kolar-Ronier-Szabo result, it's true that this is tight. So there's two proofs of this known. So the original proof by Faraday and a much later proof of Alon, Krivalevich, and Sudakov, which uses dependent random choice, which is a very useful method in extremal combinatorics. So myself and my PhD student at the time, Junkyung Lee, were looking at this theorem and wondering when it's sharp. So is it possible to improve this theorem in any particular case? And the conjecture that we came up with is the following. So again, the situation is almost the same. So for any bipartite graph, H with max degree R on one side, containing no copy of K or R. So basically what we conjectured is that in the same situation, we have max degree R on one side, but it doesn't contain the complete bipartite K or R, then the extremal number, you can get a power saving. So the extremal number of H is big O of n to the 2 minus 1 over R minus delta for some delta greater than 0, depending on H. So, okay. So why believe this conjecture? So originally the conjecture came from thinking about the fact that lower bound constructions tend to be algebraic, and algebraic constructions tend to be pseudorandom. And it seemed to us that if you had such pseudorandom graphs and you didn't contain a K or R, then it should be the case that you get a power saving. I'll say a little bit more about this as I go along. One substantive reason for believing this is that it's true when R is 2. So there's a result of myself and Junkyung Lee, which says that for any bipartite H with max degree 2 on one side.
David, there is another question. Maybe you can take a look at it.
Yeah.
Or I can read. Shall I read it to you?
No, I'll have a look.
Jacob Fox already answered it in the comments.
Oh, yeah. Okay. Okay, so for any bipartite graph with max degree 2 on one side and no C4, so not containing a copy of K22, then this does actually hold. Then the extremal number of NH is big O of n to the 3 halves minus delta for some delta greater than 0. And the proof idea, so I'll say just a short line about it. So the proof idea is a sort of structure versus randomness idea, which is used a lot in additive combinatorics, and maybe sometimes it's used in graph theory, but less so. So the idea is that you have two situations. One situation is where there is a subgraph with too many C4s. So if you have a graph which has too many C4s, then it becomes actually quite easy to build such a thing. It becomes quite easy to build the base graph H. And on the other hand, if that's not true, if there isn't some subgraph that contains too many of these cycles of length 4, then otherwise the C4s are well distributed. And if they're well distributed, then in that particular case, it also becomes fairly easy to build a copy of this H. So you get these two different situations. Our original version of this, the way in which we proved this, so we got that X. Oh, sorry, I should say something extra before I say this. So there's a restatement of this theorem in terms of what are called subdivisions. So the subdivision H prime of H is the graph obtained by adding an extra vertex on every edge of H. On every edge of H. So for example, if H was just a triangle, then by subdividing it, I just mean that I look at each edge, I put a vertex on each edge. So in that case, K3 becomes actually a cycle of length 6. So what we actually proved, so restated version of the theorem, is that for any t, the extremal number of n of the subdivision of kt, and the subdivision of kt contains every other subdivision, and the class of subdivisions is actually exactly the family of graphs for which there's maximum degree 2 on one side and there's no copy of C4. So they're exactly the same thing. So for any t, the extremal number of nkt is big O n to the 3 over 2 minus, the constant we got wasn't particularly good. It's 1 over 6 to the power of t. So in this form, it actually answers a question of Erdős. So answered a question of Erdős. We actually only realized it answered a question of Erdős about 3 months after we wrote the paper, but it turns out that this was explicitly asked in a paper of Erdős in about 1988. But also about 3 months after we wrote the paper, Oliver Janzer found a much simpler proof that gives much better bounds. So what he showed is that xn kt prime is big O of n to the 3 over 2 minus 1 over 4t minus 6. So we had this sort of exponential dependency on t, and he got this linear dependency on t. And actually, I think that this is probably sharp. So conjecture is that that actually this is sharp. And also, this is a very important conjecture. So the reason I think that this is a very important conjecture, even though the exponent looks kind of arbitrary, is that if you know this conjecture, then it's plausible, maybe, that it gives you KT-free pseudo-random graphs of density n to the minus 1 over 2t minus 3 on n vertices. So there's a paper that I wrote at some point showing that, so if you start with C6 free graphs, then you can sort of unsubdivide them to get optimal constructions of triangle-free pseudorandom graphs. And it's plausible that you can use the same method, starting with some construction for KT prime free graphs, that you can sort of unsubdivide that and get pseudorandom graphs which are KT free. And if you know that, then there's a very, very nice result, recent result of Mubai and Verstrata, showing that if you know this, then you know that the Ramsey number, the off-diagonal Ramsey number of KT versus KN is actually equal to n to the t minus 1 minus little o1. So if you have such a construction, it implies these pseudorandom constructions. And if you have the pseudorandom construction, it implies an optimal lower bound for off-diagonal Ramsey numbers. So the upper bound there is already known, but the lower bound is still open. And the actual lower bound that's known, coming from essentially from random graphs, is off this by a factor of 1/2 in the exponent. But if you know that these things exist, then you actually get the correct exponent here. So somehow solving this and showing that this is tight eventually gives you this. Potentially, it might not, depending on what the construction looks like. But it's certainly very, very plausible that it would. Okay. Let me mention a few other things in this general area. So while we're talking about subdivisions, there's another conjecture, also still open, and I think probably very, very difficult, of Kang, Kim, and Liu, saying that if you know what the extremal number of a bipartite graph is, then you should be able to tell what the extremal number of its subdivision is. So if f is bipartite, with the extremal number of f equal to big O of n to the 1 plus alpha, then the extremal number of the subdivision of f is equal to big O n to the 1 plus alpha over 2. And the thing that's nice about this, so this looks to me like a very, very difficult conjecture, but the thing that's nice about this is that it implies the rational exponents conjecture. So somehow we know the exponent for enough graphs that if you just apply this repeatedly, then you will actually end up getting the full rational exponents conjecture. Okay. However, this conjecture looks extremely tough to me. I don't see any sort of general mechanism from going from this from a particular graph down to its subdivision. In fact, it was even open, so it appears tough. They left it was even open for h is equal to kst. So the only bipartite graphs that we've known anything about for any length of time are the graphs kst when t is larger than s. And in that case, even then, we didn't know that this is true. But there's a theorem due to myself, Oliver Janzer, and Junkyung Lee, saying that actually in this case this conjecture is true. So if you take the subdivision of kst, then you get what you expect, which is n to the 3/2 minus 1 over 2s. And also that's sharp. So this is tight by the random algebraic method. This is tight when t is much larger than s. Again, we don't have any particularly good control over how this t depends on s. It's been studied for small cases. So when s is 3, there was a recent paper showing that you can take t to be around 30 or thereabouts. But in practice, you end up with something much, much larger. Okay. But coming back to the rational exponents conjecture, what can we actually say about the rational exponents conjecture? So one thing here, this is a specific graph where we get that the exponent is actually 3/2 minus 1/2s. So let's say that a rational, or an element of Q, is realizable if there is a graph H such that the extremal number is n to the r. So if you want to try and prove the rational exponents conjecture for a single graph instead of a family, then we want to show that every rational between 1 and 2 is realizable. And what we know is an ever-expanding family of these. So I'm not going to try and give a full survey of all the things that were known, but for the longest time, all that was known was 2 minus 1/s. And that's improved massively. And in some ways, the most notable theorem here now is, or the most recent theorem, is the theorem of Zhang and Chu, showing that 1 plus P over Q is realizable whenever, I think it's Q greater than P squared. Let me just check my notes. Yeah, whenever Q is larger than P squared. So quite a few exponents are known to be realizable, but the conjecture is still quite widely open. But let me give you at least the flavor of what's actually going on here. So where are these kinds of results coming from? They're actually coming from variations on this subdivision conjecture. So here's another definition. So the K subdivision HK is the graph obtained from H by adding K vertices to each edge. So before, when we just talked about subdivisions, we just added one particular vertex to each edge, and now we're adding K vertices to each edge. So we really are just sort of breaking it up, each edge, into a long path. Okay. In that particular case, there's a nice result. So there was a conjecture of myself and Junkyung Lee, and the conjecture stated that for K, is it odd? Yeah, so for K even, the extremal number of n hk minus 1 should be equal to big O of n to the 1 plus 1/k. So, in actual fact, it should be this minus some delta. So what's the thinking there? A one subdivision is just when you take k equals 2. So when k equals 2, you're getting n to the 3/2 minus delta. So here, what we're saying is, so if I take a particular graph, like, again, like a triangle, and I now, instead of taking a one subdivision, I now put 3 vertices on this, then this should have extremal number which is smaller, strictly smaller than n to the 4/3. So the extremal number of this thing should be n to the 4/3 minus delta. The way to think about this, sorry, this should be 5/4, not 4/3. N to the 5/4 minus delta. The way to think about this is if instead we had 2 parallel edges, so we had 2 vertices and just 2 edges between them, and we subdivided each of them 3 times. So we put 3 edges on each of these, then in that case, we actually end up with a cycle of length 8. And in that case, it's conjectured, whether it's true or not, I don't know, but it's conjectured that in that case, you should get n to the 5/4. The motivation then behind this conjecture is that if you don't have any parallel edges, so like here where we just have a triangle, and you do the subdivision process, then you should actually gain a delta factor. So the only case should be when you have parallel edges. In that case, you get n to the 5/4, but when you don't have parallel edges, it drops below 5/4. And I've stated this as a conjecture, but actually it was proved by, whoops, actually I can't just do that. It was proved by Oliver Janzer that this is the case. Okay, I won't say too much more about these kinds of things, but this kind of result here, where we're talking about understanding what's happening for longer subdivisions, is what feeds back into the progress on this rational exponents conjecture. So from here, you can show that various exponents are realizable, and if you use variations of this theme, you get that various things are realizable. Just this is one of the nicer results that comes out of this. One more question. Yeah, so somebody's asked, how important is it that you subdivide exactly k-1 times as opposed to at least k-1 times? The problems end up having quite different flavors. So if you're allowed to subdivide more than k-1 times, the problem actually becomes easier. And actually, if you have no upper bound at all, then it will drop to linear, just because you can get logarithmic paths going between any two vertices. So really, it's important that you nail down the exact number. Okay, so before I move on, I just wanted to say one last thing about this, which is actually there's a version of our original conjecture that was proved by Sudakov and Tomon. So Sudakov and Tomon have shown that for any bipartite H with max degree OR on one side and no K or, then the extremal number of NH is, so the conjecture was that you would get a power saving on this, but actually what they show is you get some little O term. And the proof relies upon hyperregularity, so the little is like some inverse Ackermann type thing. So it's a very, very slowly growing function. I should also mention that something very, very close to this is implicit on a paper about Burge hypergraphs by Balko, Gerbner, Kang, Kim, and Palmer. Okay, so that's where it lies. And I would like to see, well, I'd like to see two things about graphs. One is I'd like to see this improved so you actually get a power saving here. It seems kind of difficult to do this. Certainly using hypergraph regularity is a long way from that. And the other thing is I'd like to see, and I feel like we're reasonably close to solving the rational exponents conjecture. Okay. All right. So to finish up, I want to say a few bits and pieces about some very recent results, which are closely related to this, but they're about hypergraphs rather than about graphs. So, so for the most part, I'm going to talk about 3 uniform hypergraphs, so where every edge has size 3, and we'll see how we get along. So one thing that I've already noted is that the rational exponents conjecture, or at least the second rational exponents conjecture, where for any graph H there should be an exponent, is false for hypergraphs. And the reason for that is because of this classical example. So the extremal number of if you take two graphs, one of which is just two edges sharing a pair of points, and the other is a triangle. So if you ban both of those, then in that particular case, it's known that the extremal number is little o n squared, and it's also close to n squared. So, and actually it's known if you go to higher uniformities, if you go to like uniformity 5, it's known that you can take a single graph for which this is true. Okay. All right, so the thing about this is this particular thing, so the rational exponents conjecture, as I said, is false, but this particular thing is a special case of what's called the BrownRedux problem. So, so the BrownRedux problem is the following. Let Fn VE be the maximum number of edges in an n-vertex 3 graph, or 3 uniform hypergraph, where no E edges span at most V vertices. So this thing here, this extremal number of the two things I drew above, so the thing where you have two edges sharing a pair and you have a triangle, that extremal number is actually just the same thing as Fn63. So because we don't want 3 edges on at most 6 vertices. And clearly this configuration here has exactly 6 vertices and 3 edges, so we don't want that to be there. And if you get this configuration here, then it's easy to add another. Basically, if you add another edge connected to it, that's a 6-3 configuration. So you don't want either of those. And so in this particular case, we know that this extremal number, this thing that contradicts this rational exponents conjecture, has Fn63 is equal to little o n squared. This is a very classical theorem due to Rouge and Semerady, which is connected to all sorts of different themes. So it's connected to the graph removal lemma, it's connected to the induced matching lemma, it's connected to Roth's theorem. It's a really very, very classical thing. There's also a conjecture that generalizes this. Sorry, there's lots of things going on in the chat I haven't seen. Okay. All right. All right, so the conjecture, which it's usually called the BrownRedux conjecture, but it was stated sort of gradually over time. And the conjecture is that Fn E plus 3E is equal to little o n squared. So in particular, we have this conjecture that Fn 7,4 is equal to little o n squared, which is usually just called the 7,4 problem. So what that is really saying is either you find two edges which share a pair, or the graph is linear, so that means that the hypergraph is linear. So any two edges share at most one vertex, and you don't contain this particular thing. So that's a linear hypergraph with 7 vertices and at most 4 edges. And we don't know this. We know if we could prove this, it would imply Semerady's theorem for length flow progressions, for example. And the same is true if you could prove it for E, then you would get Semerady's theorem for length E progressions. Or at least that's claimed. I don't know if it's actually written down anywhere. Okay. So what these actually know, and I say that this is tough. This is a really hard conjecture that nobody knows how to solve. But there is a nice theorem of Sarkozy and Selkov from about 15 years ago. saying that instead of getting e plus 3, if you add a log factor, so what they get is basically if you add log base 2 of e instead of 3, then in that particular case you get little o n squared. So so if there's no e plus log e vertices containing e edges, then you have little o n squared. So one of the results that I wanted to mention, and I won't say too much about it, is a theorem by myself, Lior Gishberliner, Yevgeny Levinzov, and Asaf Shapira, improving this. So saying that actually Fn e plus, so it's some constant times log e divided by log e. E is equal to little o n squared. So so this doesn't look like a huge improvement. Essentially what we're doing is we're improving a log e here to a log e divided by a log e here. But a lot is needed to convert this to this. So for example, this proof on top, what it really uses is repeat applications of the graph removal lemma. Whereas this thing on bottom uses applications of the hypergraph removal lemma for every uniformity. So really what you're trying to build is, the situation is basically the following. So you have a graph. The graph has delta n squared edges. Sorry, that's a 3 graph. So you have some 3 uniform hypergraph with delta n squared edges. And what you want to do is you want to build a graph that's as small and dense as possible. And one way to do that is to keep applying the removal lemma. So if you keep applying the removal lemma, it basically tells you that if you have some configurations, then you can glue those configurations together to get some denser configurations. And if you repeat that, then you get this e plus log n, this Sarkozy-Salkov. What we do is we do a similar gluing operation, but at each step, instead of using the graph removal lemma to do the gluing, we use the hypergraph removal lemma to do the gluing. The actual precise nature of it is it's much more complicated than what Sarkozy and Salkov do. So you can write a proof of Sarkozy-Salkov in about 2 pages, whereas it took us maybe 25 pages to do this gluing with hypergraph removal. And given how much that goes into it, it seems like this is a very natural cutoff point for this. So I'd be very interested to see some improvement in this. Okay. Part of the reason, though, that I mentioned this BrownRedux problem is because it relates to some recent results by myself and Jacob Fox and Benny Sudakov and Yufei Zhao, where we prove that Fn 10(5) is equal to little o n to the 3/2. Okay, so just floating there like that doesn't look so interesting. So I want to try and justify why this is an interesting result. And what I'm going to do is I'm going to rephrase it in a different form that makes it look more interesting. So, so if you recall, a Burge cycle is a sequence of vertices and edges. So V1, E1, V2, E2, up to VK, EK, where the ith edge, EI, contains VI and VI plus 1. So, so essentially what it is you just take a cycle and then, assuming that it's a 3 uniform cycle, basically the 3rd edge can go anywhere for each of these edges. So I could put it there, or I could make it actually be one of the other things within the cycle. So it's a cycle where we extend each edge to, it's just a graph cycle where we extend each pair to a 3 edge. Okay. So in this terminology, what we've actually proved is something about the girth of graphs with respect to these Burge cycles. So HNG is the maximum number of edges in an n-vertex 3 graph.
Sorry, David, can you take a look?
Yeah, I'll tell you just, let me just finish this definition and then.
Sure.
So somebody's asked if this method that we used above for proving this follows a result of Yoji Shoimoshi. And there is some justice to that. So the first result in this direction was a paper by Shoimoshi and Shoimoshi showing that you could improve the Sarkozy Selkov bound in a particular case. So they use the 3 uniform removal lemma to get something extra on the next step. But the actual details of then extending this to higher uniformities, so the idea, the roots of the idea certainly are in this paper of Shoimoshi, but the actual details of managing to push it and getting it to extend to all uniformities, it becomes very, very difficult. So yes, there is some justice to this idea that it comes from their paper. Okay. All right, so I was talking about Burge cycles, and basically I'm talking about girth. So what's the maximum number of edges in a 3 graph with n vertices where the girth is at least g? And you have to be careful here in terms of what you mean by girth. So for example, that means that you don't contain a Burge cycle of length g or less. But that already means that we're banning 2 edges that share two edges that share a pair. Because 2 edges that share a pair are a cycle of length 2. A cycle of length 3 is then just this, and you can keep going. So actually, just by what I've drawn here, so this is 2 and 3, we can see that actually Hn of 3 is again just Fn63, which is little o n squared. So Burge cycles, graphs with Burge cycles of length, no length 2 or 3, no cycles of length 2 or 3, have little o n squared edges. And the question is, can you extend this? So what happens for higher things? So if you ban Burge 4 cycles, then it's known, it's quite an easy argument. Essentially, you're just lifting the bound for C4 to this to show that you can have at most n to the 3 over 2 edges. And actually, it turns out that what the easy bound is that it jumps on every even number. So for 4 cycles, it's n to the 3 halves. For 5 cycles, it was known also to be big O of n to the 3 halves. For 6 cycles, it jumps down to n to the 4 thirds. For 7 cycles, again, it sticks at n to the 4 thirds, and so on and so forth. So you keep dropping at every even number. So the next step, it goes 5 over 4, 5 over 4, 6 over 5, 6 over 5, and so on and so forth. But there's a fairly long-standing conjecture saying that, well, up here, if I add in Hn2 is also big O n squared, because there can be at most n squared 3 edges if they don't share an edge or don't share a pair. But in that particular case, Hn2 is big O n squared. Hn3 is also easily big O n squared. But this Ruggius-Samorati result shows that it drops to some little O n squared. And a similar thing can be conjectured here. So you could conjecture that on this side, these all become little o's. And what we show is, so a thing that's equivalent to the theorem I stated above, is that actually this hn5 is little o of n to the 3 over 2. So really the question is about the girth problem within hypergraphs. In actual fact, what it's really about is about a sparse removal lemma. So we have a theorem which says that an n-vertex graph with little o n squared c4s and little o n to the 5 over 2 c5 can be made c5 free by removing little o n to the 3 over 2 edges. So the classical triangle removal lemma says that if you have n vertices and you have little o n cubed triangles, then you can remove all triangles by removing little o n squared edges. This is a version for C5s, except the density drops. So the sort of natural density here is P equals n to the minus a half. And if you think of that, then this is actually little o of p to the 4 n to the 4. This is little o p to the 5 n to the 5, and this is little o p n squared. So it's a sort of sparse removal lemma saying that if you have few C4s and few C5s, then you can remove all C5s and actually all triangles by few edges. And that has various implications. One of the implications being this result about Burge cycles, another being it's equivalent to that FN105 question. Lior Gishboy-Liner asked, is it the case that HN5 is it the case that this thing is essentially sharp? So here's a conjecture that HN5 is n to the 3 over 2 minus little o1. We don't know, actually. My expectation is that the answer should be yes, but we struggle to get a construction. So some of the other applications in our paper, we managed to get constructions, but for that particular thing, we didn't actually manage to get a construction. So I'm not sure. I would conjecture that there should be such a construction, but I don't see how to do it. The last thing that I mention is that this has some arithmetic consequences that sort of hark back to things we were talking about earlier in the graph context. So let's define, so we can define an extremal number for equations. So if we have, let E be a linear equation. Then the extremal number of NE is the largest number of points or elements in a subset of 1 up to n containing no non-trivial solution to E. What I mean by non-trivial can change depending on the equation, but for example, if you take E to be x1 plus x2 is equal to x3 plus x4, then the trivial solution is just when the set x1, x2 is equal to the set x3, x4. Or when, for example, E is the equation x, let's call this E1 and E2. x1 plus x2 plus x3 plus x4 is equal to 4x to the 5. All we want is essentially that all the equations, all of the x's are different. So trivial is all xi same. You can actually insist in what follows that all the variables are different, but the real trivial case is this. And actually, for these two things, the extremal number of E1, the Seedon equation, is known to be theta of square root of n. So in fact, it's known to be 1 plus little o1 times the square root of n. So you can actually do something very, very precise there. So if you contain more than root n elements, then you get a copy of, you get a solution to x plus y is equal to z plus w. And if you're below root n, then you can find constructions with around root n that don't contain any solutions. For E2, this thing here, this is a translation invariant equation. So the answer is known to be little o of n. So there's an extension of Roth's theorem showing that for any translation invariant equation, you can find non-trivial solutions when you have little o n elements. In fact, you can gain a log factor, so you can get n over log. And that's known to be sharp. So it's known that the lower bound there is n to the 1 minus little o1. So it's also equal to omega of n to the 1 minus little o1. Okay. So the reason I mention all of this is that there's another theorem which follows from these things I've mentioned by myself, Jacob Fox, Benny Sudakov, and Yufei Zhao, showing that actually the extremal number of these two equations together, E1, E2, is equal to little o of the square root of n. So the point of this is that compactness fails for linear equations. If you remember, the compactness conjecture was that xn of a family of graphs, h1 up to hk, should be equal to theta of the minimum over I of the extremal number of nhi. And you could conjecture a very, very similar thing for equations. So you could conjecture exactly the same thing for linear equations, that the extremal number for those linear equations is determined by the minimum extremal number. But for these two equations, the minimum extremal number, this is close to linear, and this we know is actually root n. But this result says that if you want to avoid solutions to both equations, so both the Seedon equation and this translation invariant equation, then in actual fact you need to drop to little o n. So just harking back to what we were talking about earlier, compactness fails for linear equations. And I also expect that it fails for graphs, but we don't know how to prove that. Okay, so that's basically all I wanted to say, so I will stop there.